had some audio issues when I recorded this lesson yesterday during class, so we're going to give this a go again. Try to do this quickly, but a brief overview of what we did in class for section 5.1, Antiderivatives, day 1. Goals here would be to understand the reverse process of differentiation. We're basically going to undo derivatives. Not that we're going to unlearn or take them apart. We're going to do the process, the backwards thinking process of finding a function if we know its derivative. So we're going to look through some basic rules and formulas for antiderivatives, and we're going to look at the definition and notation for the antiderivative. So here's the idea, real quickly, the definition of an antiderivative, and here's a new name. Capital F is going to be what we're typically going to use for the name of an antiderivative. If a function was g of x, its antiderivative would be capital G of x. So moving forward, be very careful about lowercase letters versus capital letters, because from this point forward, they are going to mean something different. So a definition, a function capital F is an antiderivative of a function lowercase f on an interval, provided that the derivative of capital F is equal to the lowercase f. So this is the function, and capital F is the antiderivative, and this prime is notation for the derivative. So the idea there is if you have an antiderivative, you take its derivative, you'll get the function back. So the idea is that antiderivatives and derivatives are related in that antiderivatives of a function is related in a way that we're familiar to. So the idea here is, starting with some pretty basic functions, a process might be to kind of guess and check at this point to see what the derivative might be. If I have a function f of x equals x, which is linear, we know from derivatives, if my goal, let's back up here, it says find the antiderivative. So if I have f, I'm looking for the function that has x as its derivative. So I'm looking for a capital F of x function. And we know that linear derivatives come from quadratic functions. So it might be reasonable to start with something like x squared. Now, the most efficient way to get an accurate answer is to check the antiderivative that you think is correct by taking its derivative based on the definition. If f is an antiderivative of f, so if x squared is an antiderivative of x, then if I take the derivative of capital F, then I should get the original function back. And we know from derivatives that the derivative of x squared is 2x. And 2x is not what we want. We want x. And we're off by a factor of 1/2. So the easiest way to take care of being off by a factor of 1/2 is to divide by 2. Now, the other thing here is that we should be able to find a general rule for the antiderivatives. And there are a lot of functions that will also have x as its derivative. X squared over 2 plus 7, x squared over 2 plus 15. Any constant value added to that function will give us the same derivative, x. So what we do then for notation is we will add what's called the constant of integration, and it's typically denoted with a capital C. That constant value will allow the function to move up and down on the graph and still have the same derivative. Okay? Really important that you bring that along, that C value along every time. So using that idea in your mind, you can just go ahead and pause and check this if you'd like, but I'll go forward with x squared. If we're dealing with x squared, we know it had to come from a cubic function because the derivative of a cubic is a quadratic, but we also know that the derivative of x cubed is 3x squared, and we don't have a 3 in front of our x squared in this problem, so we're going to divide by 3, and we're going to add the constant of integration. Similar idea here. With x cubed, we're going to move to a quartic, divide by the quartic, or divide by 4, and then add c. So in general, we are using what is called power rule for antiderivatives. And power rule for antiderivatives is basically the opposite process of power rule for derivatives. Keeping in mind, just going back, let's talk derivatives. Okay? If we had something like 6x to the 5th, if we wanted to differentiate Step 1 was to multiply the coefficient by the exponent. The second step then, that would give us 30 as a new coefficient. The second step then was to subtract 1 from that exponent, which then gives us a result of 30x to the fourth. And we're comfortable going in the derivative process. Now, if we were to go the other way and we were to do an antiderivative, if we start with 30x to the fourth and we need to get back to 6x to the fifth, the first thing you're going to do, you're going to undo this process in reverse order. So you're not going to do the division first. You're going to undo the subtraction first. So the first thing we're going to do is add 1 to the exponent. That gets us to 30x to the fifth. And then we're going to divide by that new exponent. And we're going to get back to 6x to the fifth. And you'll notice that these operations are inverses of one another, so we're going backwards. So in general, the power rule, if we have f of x equals x to the n, the antiderivative of that is going to be x to the n plus 1 divided by n plus 1 plus the constant of integration. A couple of graphs just to kind of show you. When we find an antiderivative f of x and we add that c thing at the end to it, that constant of integration, we found a family of antiderivatives. And any one of those antiderivatives could have come from that same f function. And nice little visual here. And you can draw some tangents here to show that if I look at any one of these functions and I were to look at the derivative at the same x value and draw some tangents, every one of those tangents, if I'd done this a little more carefully, every one of those tangents should have the same slope. So that constant value allows you to have an infinite number of antiderivatives. And that's really important to understand right now, because there are derivatives. Really important at this point to know that an antiderivative is a general rule, is a family of antiderivatives. So, using that idea, we need to be able to recognize a handful of familiar functions. Okay, and the question is, if I want an antiderivative, I want f of x, I need to be able to recognize for each of these functions where it came from. So the first one, 3x squared, we know it came from a cubic, and any time we have a polynomial, we can use power rule. Anytime I have a term in the form ax to the n, I can use power rule. So this polynomial, I'm going to take that rule, it's 3x, add 1 to the exponent, and divide by the new exponent, add the constant of integration. Simplifying, that's x cubed plus c for the antiderivative of 3x squared. Okay? 1 over 1 plus x squared, good news, there is no such thing as a quotient rule for antiderivatives. You don't need to undo low d high less high d low down below low squared must go. You need to recognize that that is a special function, and that function is tan inverse of x. So that antiderivative would be as shown. Okay? Nice little trick for sines and cosines. Sines and cosines we know are their own derivatives, with the one exception that there's that -1 factor involved. So what I like to do with sine x is I'll just write the word cosine x and then I'll check to make sure it's the derivative. Cosine's derivative is not sine. Cosine's derivative is negative sine. So I can't change the original function. I need to put a negative. Let's write this down here so you can see it. I need to put a negative on the cosine, on the antiderivative, in order to get the sine back. And then secant squared, I hope you've all recognized at that point, is the derivative of tan. So the antiderivative of secant squared is tan. Some important relationships that you're going to need to recognize here kind of moving forward. One other thing on notation. We already talked about how capital F is used to name an antiderivative. Kind of like F prime was used to name a derivative. Okay? Now, with derivatives, we had an operator. The operator for derivatives was d dx. That's an operator. That tells us that you're about to find, or it's kind of a command or an operator that says find the derivative of. We need an operator for integration. Integration. I need to introduce integration. Integration is the process of finding the antiderivative. To find the antiderivative, you're finding the indefinite integral. The command is to integrate. And the symbol for integration involves kind of a long stretched out s and a with respect to x, a dx at the end. You don't need to underline that. You probably shouldn't. But if I wanted to find the antiderivative of 3x squared, I would use this notation, the command or the operator being that symbol tied to the dx, because with respect to x is really important. Okay? So, power rule, we already talked about. I'll kind of let that stand for right now. That's in your notes. Take a look. I'm going to skip the proof for the moment for time purposes. We'll have a chance to get to that a little bit later. A couple of rules that are important that will help you, and I think these are pretty self-explanatory and consistent with the derivatives. If I find the antiderivative of 3x squared, we already did this one, so this would be x cubed, right? Dx. That would be x cubed. I could have also done that same problem by putting the 3 out front and done the derivative of x squared. And I know this is example, it's not proof, but this would be 3 times x cubed over 3, which would then end up with the same as what we did before. So a constant, you can take the constant out and put it in front of the integral and then do the integral of a simpler function, or you can use kind of power rule the way we talked about it. The sum rule allows us to do what we do with polynomials. Okay? The idea is if I have an integral of 3x squared plus 6x plus 8, what allows me to do this sum rule allows me to break it up into 3 different integrals. Now, I don't normally, got to put a dx there, I don't normally write all this out when I do it because it's easier to do in my head and integrate each part instead of rewriting the symbols. And I think you'll understand that as we go here. And there's a good example of that right now. It says find the following antiderivatives. Okay? So we're finding the following antiderivatives. We're looking for the name of the antiderivative, which is capital F of x. This is a polynomial. We are going to follow the sum rule, and we're going to follow power rule. Okay, so 3x squared, and here, this is my process for power rule. Many of you can do this faster than I, but with 3x squared, I'll write the coefficient, I'll write the variable, I'll increase the exponent by 1, and I'll divide by the new exponent. I'll do the same thing with the second term. 10x to the first becomes 10x squared, got to divide by 2. 7 is a constant term, and constant terms come from linear functions. We'll add a c at the end. So I think it's a good idea to simplify your answer here. This would be x cubed plus 5x squared plus 7x plus c for the antiderivative of the polynomial given. Okay? One important piece to day 1 here is recognizing when you can and cannot use power rule. And for the most part, the same rules apply for derivatives as they do for antiderivatives. So if I can write a function, if I can rewrite this function in terms of a coefficient, a variable, and an exponent, I can use power rule. So this function is also that function. And we'll then go ahead and use power rule on each of those terms. And we'll get capital F of x is equal to 1 times x to the negative 2, because I add 1 to the exponent, I divide by the new exponent. 6x, add 1 to the exponent, divide by the new exponent, add c. And I think it's a good idea to simplify. But for nothing else, it's very good algebra practice. It's not wrong if you don't. I just think it's easier to use down the road if you do. So this would be negative 1 over 2x squared minus 1 over x to the 6th plus c. Okay? Again, be able to recognize when you can use power rule. And as mentioned earlier, there is no such thing as quotient rule for antiderivatives. We will do some advanced integration techniques later on, but you need to know right now that you don't have to undo low d high less id low. Down below, low squared must go. So this is a fraction that needs to be simplified first. And this is a single term denominator. If you had me first semester, we talked about single term denominators. Denominator. Spelling is a good thing. Single term denominator. And if you have a single term denominator, you can write this fraction as three different terms. You could write it as 4x to the 6th over x to the 5th, 3x to the 5th over x to the 5th, and 8 over x to the 5th. That's all. This is all still f. We haven't done any calculus yet. This is the same as 4x plus 3 minus 8x to the negative 5th. And then to find the antiderivative, we would use power rule in each one of those terms. 4x squared over 2, 3x to the 1st over 1 if you want to do power rule that way. Otherwise, you can recognize that it's linear, minus 8x to the negative 4th over negative 4. Add the constant of integration. We would simplify 2x squared plus 3x plus 8 over x to the 4th plus c would be our antiderivative there. Okay, two more quickly here on day one. We're not going to apply a chain rule aspect to this yet. The key to today and the next couple of days is you need to simplify first. This is a FOIL away from being a polynomial. So we're going to go ahead and make it a polynomial because power rule is really cool. So this would be y to the 4th plus 8y cubed plus 16y squared. And you would then integrate with respect to y. Notice I should have made a point of this earlier. We're using y's now instead of x's. Okay? So this antiderivative then would be y to the 5th over 5 plus 8y to the 4th over 4 plus 16y cubed over 3 plus c. Simplify that middle term as appropriate. Okay? Last example. Nice thing to know that fraction exponents also can be used with power rule. I think that using the idea of writing the coefficient, writing the exponent, or writing the variable, increasing the exponent, 2/3 plus 1 is 5/3, right? And then I'm going to divide by 5/3. A lot of those with nice integer values you can do in your head. I don't think you can. Well, I shouldn't assume you can't, but this one's a lot more difficult to do in your head. Dividing by a fraction is the same as multiplying by its reciprocal. So this would be simplified to that value for the antiderivative. Right? Homework is day one. We're going to move on to day two today for the interest of time, but you want to make sure you try some of those problems. Day two is about recognizing some things. Antiderivative of sine. We talked just a moment ago about the relationship between sine and cos, and I think it's really important that we try to write and do the derivative, because I think derivatives are a little bit more comfortable. So the derivative of cos is not sine. The derivative of cos is negative sine. So I'm going to put a negative in front of that cos, and now we're good. That integral is for the sine function. Okay? Same idea here. Is the derivative of sine equal to cos? Yes, it is. So I'll add c and call that the antiderivative of, or the indefinite integral of cos x. Okay? Don't really want to get into chain rule, but if the inside function is linear, you can kind of apply a chain rule idea, and using that guess and check that we just talked about is a good idea. So let's take a look. Sine goes with cos. Now the derivative of cos is negative sine, so I need a negative on the front. And again, we talked with chain rule, whenever there's an inside function, that inside function needs to be left alone whether you're differentiating or anti-differentiating. And then we're going to double check, because this looks good at this point for the antiderivative, but I want to double check to make sure. The derivative of cos 3x, the derivative of negative cos 3x is sine 3x times 3, because of that chain rule piece, right? Now, this is 3 times bigger than this. So what do I have to do to my antiderivative to make it right? I have to make that a 1/3 in front. Let's clean that up just a little bit. I need to divide by 3 or multiply by 1/3 in order to make that antiderivative correct. Same idea here. Sine and cos go together. Let's make sure the signs match. Derivative of sine is cos. There's a negative up here, so I need a negative down here. Leave the inside the same and divide by the inside. So this would probably concisely, that's not a cos problem. This would be negative 2 sine x over 2 plus c. Okay? And here's a table of some of those trig ideas. I'd like you to practice some of those on your own. Here's a special one you need to recognize. I don't like this way it's written here, but it could be written that way. If you see it written that way, I would write it as 1 over x dx. And based on what we just talked about, power rule looks pretty tempting. This is x to the negative 1, and if I apply power rule to that, I end up with x to the 0 over 0, which has obvious problems. So that, because anything divided by 0 is a bad idea. But if you pay attention, you should recognize what function has 1 over x as its derivative. It is the natural log function. And as a little caveat, you need to put absolute values on the natural log function because the domain of the natural log function is real numbers that are greater than 0. You can't natural log a negative number, so we need absolute values on that. E to those are our favorite functions. E to those are their own derivatives, but we understand that chain rule piece, the a is a multiplier, so the derivative of e to the ax is a e to the ax, and we don't have that a on our original function, so we need to divide by it. So it's e to the ax divided by a plus c, kind of like what we did with the trig functions not too long ago. Same idea here with c. I think this is a good place to apply the sum rule, because when you're applying different rules to different parts of a function, I think it's nice in your mind to separate them out. If you don't need to, don't worry about that. But here we have e to the 2t has an antiderivative of e to the 2t divided by 2. 2t to the 1/2 has an antiderivative of 2t to the 3/2 divided by 3/2 plus c. I used the rule for e on that function, and I used power rule on that portion. Okay, so this would be 1/2 e to the 2t plus divided by 3/2 is multiplied by 2/3. Hopefully that gives you a good overview of those types of functions. And then there's a little set of definitions there for you straight out of your textbook. Here's your homework for day 2. Like you to go through a lot of these problems. I think practice is really important. It's hard to get good at these things and writing the notation if you don't actually do it. So please practice the notation, practice the name, and all those wonderful things. Thanks.